Hello and welcome back to the Coking.com YouTube channel. I'm Evan Hyde. I am here at Berthold in Germany. Very excited to be here with my friend Marcel. Marcel, introduce yourself a little bit to our audience, please.
Yeah. So my name is Marcel Fröhlich. I'm the head of the process control division. And yeah, I'm very glad for being able to welcome Evan today at Berthold at our premises. And yeah, we will talk about some very exciting things regarding NDT and how you can avoid it in a refinery.
So thank you for that introduction, Marcel. So NDT, we talk about non-destructive testing. Many of you who are watching this video probably know what this is, but just by way of introduction, NDT testing happens all around our facilities all the time. It can be a variety of different types of testing, but the one we're most concerned with as it pertains to this level instrumentation is X-ray. So X-ray is something that's often done on welds, various, piping, pressure vessels, whatever. You want to make sure the quality is good of that weld, so you'll actually shoot an X-ray across it, look to make sure the quality is tip-top. Now, this is very important. We have to do it for the safety and integrity of our process. Unfortunately, has a negative impact on some of our level instrumentation. So, Marcel, could you explain to us a little bit about how the level instruments actually work and why does X-ray actually interfere with them?
Yeah. So this model is very nice to explain the basic functionality of a radiometric level system. So you have on the one side, you have a radioactive source that is shielded with a kind of fan beam outlet, fan beam collimator. In this case, it is emitting a 45-degree angle for the radiation. And then on the other side, you have a rod detector, a rod scintillator, and this scintillator detects the intensity of the radiation. So once the level is rising of the liquid or the solids you have inside the level, more and more radiation is blocked. So less and less radioactivity is arriving at the detector and can be measured by the same.
So that's the count rate, right? So this, if you've seen some of our other videos that we've produced here with Berthold, you'll see that the amount of radiation is detected as counts, and as you block that radiation, the count rate actually goes down because it's getting less radiation. Is that right?
Yes, exactly. So the more radiation arrives at a detector, the less or the lower the level is inside the vessel, and the less radiation or the less counts you get at the detector, the more or the higher the filling level is in the vessel.
So that's how the instrument reports back. Yes. 71% level is actually a lower count rate than the empty condition.
Yep.
Right? So when somebody does an X-ray NDT inspection, that generates a lot of radiation. And how would that impact this instrument?
I mean, if you have no protection or no compensation against that NDT, the detector will suddenly see a steep increase of radiation. And we just learned that more radiation at the detector means less level. And so without a compensation, the level reading would go suddenly down.
And it can happen almost instantaneously.
Yes.
Like I've seen it before in the plant when the level is 74% and next thing it goes whoop, all the way down to zero, poof, gone. And we know that's not possible. So normally the board operator would be like, okay, well, who is doing X-ray nearby? But it's something that should be regularly communicated ahead of time, but not always the fact. But you have some technology that actually manages this change.
Yes. So, basically explained, our detector sees or recognizes when such an NDT event is happening. And then the measurement signal freezes immediately so that the customers are not getting any false reading in their DCS. And once the NDT is over, the signal goes back to the normal real level.
Yeah, so it senses a rapid change and it's like, okay, that's not real. I'm just going to keep on reading the same. And we're going to talk a couple of use cases in delayed coker land here in a second. But one of the things that is surprising to me, and you guys have done some really interesting math to indicate really how far away this X-ray inspection will be happening that can influence these things way up in the coke drum structure or perhaps on the main fractionator. How far do these X-rays actually travel in a way that can impact the instrument?
I think what many people don't know is that this X-ray can travel really far. So, for example, if you do the NDT testing with cobalt source of 100 curies, which is quite typical, this radiation can travel without any problem 1,600 meters. And after this 1,600 meters, it still has influence to our level reading here.
So for my friends in the US, 1,600 meters is conveniently almost exactly 1 mile.
Yeah.
So I think this is relevant because, if you're a small plant in the middle of, nowhere, then you may not have a lot of activity going around you, and you're probably aware of all the NDT that's happening inside your facility. But if you're in an area that's more congested, such as the US Gulf Coast, or perhaps up in Rotterdam, or maybe in Singapore, where there's a whole lot of plants tucked into a very small area, there could be something happening outside of your fence line, and the delayed coker is way up in the sky, and they could be shooting a beam of radiation from a surprisingly far distance away that could be affecting us. So I think that's really interesting, and I'm definitely going to take away that math. I'm finding it to be very useful. So the X-ray protection is something that looks at this quick drop, right? So the two places in the delayed coker where we typically have gamma radiation instrumentation is in the coke drum and in the main fractionator, right? So let's talk about each of those specifically. In the coke drum application, how do you think it would behave with this X-ray protection and without it?
Yeah. So basically, there are two ways or how the detector algorithm is doing this X-ray protection. The one is the so-called hard mode. So usually, or as per standard, the limit is 150% of the total empty count rate. So when 150% of the total empty count rate is exceeded, the detector goes in NDT mode or XIP mode and freezes the measurement signal immediately. The second method is the so-called soft method. It is more like that it can be adjusted by the customer. So the detector is looking at the count rate change in a certain time. So if you can, you can compare it, maybe the count rates with the velocity, and then this count rate change per time can be seen as the acceleration. So when the detector sees an really extensive acceleration of count rates, which is untypical to this process, as I told you, the customer can set this values by himself to make it really fit to his special process, then detector also goes into the freeze mode.
In freeze mode.
Yeah.
And I think that that's really interesting to think about because the so-called hard versus soft sensors, right? Because, like in that example I mentioned before, if it goes from one level down to 0, something's wrong. It's not physically possible. But if that beam of radiation is just coming maybe nearby and you're just getting touched by a little bit of it, it can just sort of drift that reading down low. But if that acceleration is faster than is physically possible, the instrument also freezes.
Yep.
Okay. So I think that that's really interesting for our specific application in the delayed coker, in particular for the main fractionator, because that's a spot where we often will specify nuclear instrumentation, a level instrumentation on the bottom of the fractionator, and that's probably one of the most critical spots for us to know the level, right? And if that level all of a sudden starts dropping low, one of two things are going to happen, right? The control valve coming into the main fractionator is going to go wide open, and the level is actually going to go high. And for those of us in delayed coker world, that's very bad, because if that level goes too high if it blocks the coke drum vapor line, all kinds of bad things can happen. So we don't want to do that, right? Or consequently, if the operator maybe is necessarily aware that this is happening and maybe takes control of that feed control valve, the level starts dropping low, then you can have cavitation, you can have problems with your heater charge pump, you can have all sorts of negative downstream consequences. So not only is it important to have this so-called hard stop for the very immediate step changes in radiation, these smaller ones I think are just as important to be aware of.
Yeah.
So your software has this functionality built into it, and it comes basically standard in all the installations, right?
Yes. I mean, that's the great news. It is really built into each and every detector, and it just needs to be activated in the software by the customer.
And it can be configured too, right? So we were talking about, what is this rate of change that's reasonable? And this is something that you have to do some math on, how big are your pipes, how big are your pumps, what's the resonance time, all these things need to be thought about.
Yep.
And then you can say, okay, a certain amount of counts change per unit time, per second, per minute, whatever, that triggers this soft setting.
Yeah. And so, I mean, the combination of these two methods should really give you, the possibility to have really a reliable protection against NDT.
Some assurance that, you're not going to make a bad operational decision based on a faulty reading.
I think that would be worst case scenario.
Yeah. Okay. Well, perfect. Well, we appreciate Marcel taking time to explain this very interesting topic to us. I think in our world, NDT and X-ray happens all the time, and it's important that you make sure that your level instrumentation has this type of functionality, because it can definitely save your bacon, right?
Yeah. Also, thank you for coming.
Thank you, Marcel.
It was great to have you here.
Perfect. We really enjoyed it. Thank you for enjoying our video. Check back at our YouTube channel, learn more about all sorts of exciting delayed coker technology. And thanks for our friends at Berthold. Talk to you later.